This presentation will deal with the lattice structure, and indeed this is a part of a wider project that is carried out in collaboration with the CIRA, that is the Italian Center for the Aerospace Research. In this work, I will present a model, a numerical model that has been used to predict the flexural behavior of lattice core specimen. In particular, in general, the behavior of cored structure is studied, but the out of plane flexural behavior. That is, the load is applied on a plane perpendicular to the plane of the along a direction perpendicular to the plane of the specimen, of the skins of the specimens. In this case, the load is applied along a direction that is parallel to the plane of the skins. Here there is the outline of this presentation. First of all, there is the presentation of the case study. In particular, the geometry of both the specimen and of the cell that constitutes the lattice, the core lattice, is defined in terms of geometry and in terms of dimensions, together with the material. Moreover, also more details about the test scheme is furnished. Then there is the presentation of the numerical model, in particular, how the domain was discretized, the properties of the material adopted for the simulation, and the boundary conditions considered in this case. Then the model has been validated against results from experimental tests. So this experimental section is showed. In particular, both the manufacturing of the specimens that have been produced through ABM, that is an additive manufacturing technology, together with the test, the 3-point bending test that has been used to load the specimen. Finally, there is the presentation of the results, so the validation of the model, and there is also the presentation of a fractographic analysis to delineate the failure modes, and also an microstructural analysis to delineate the characteristics of the printed material. Here there is the specimen. It is composed by a core whose dimensions are 30 millimeters by 10 millimeters by 9 millimeters, and two faces are covered with the skins. The thickness of the skins is 1 millimeter. I cannot use the term upper and lower skin in this case because, as we will see, the specimen is loaded on the side. So it's not it makes no sense to use this terminology. As concerns the base cell that is used to produce the core, it is an octet truss cell. It is composed by a face-centered cube on the outer part of the cell. In particular, each face of the cube is composed by 4 beams that are arranged in an X shape. While in the inner part, in the inner volume of the cell, there is an octahedron composed by 12 beams, and here is highlighted in red. The side, the edge of the dimension, the length of the edge is 6 millimeters, while the diameter of the beams is 1 millimeter. But these are nominal dimensions. We will see that during the process they will change. The process tends to produce a thinning of the geometries. As concerns the material. The raw material is a powder, a titanium powder. In particular, the titanium 6Al for vanadium has been used. That is called also titanium 64. And is a common an alloy commonly used for aeronautical applications. Here there is the test setup. It's a 3-point bending test. The load is applied in the same plane, in a direction contained in the same plane of the skins. So the skins are on the lateral surface of the cores in this case. The distance of the supports is 20 millimeters, while the loading speed, so the rate of the loading nose, is 2 millimeters per minute. Here's some information about the numerical model. For discretize the domain, only beam and shell elements have been considered, so not 3D elements. In particular, 1,364 beam elements have been used for the core, while 1,344 shell elements have been considered for both the skins. As we can see here, the diameter of the beam, of the simulated beam, is 0.8 millimeters, while the thickness of the shell elements is 0.8 millimeters. So there is a thinning of about the 20%. And this is a problem, let's call it with this term, a problem of the process that tends to shrink the geometries. To determine this value, we have used a trial and error procedure based on the weighting of a real specimen, and then trying a suitable value of the geometries, of the dimensions of this particular, to catch the real weight, of the specimen. So it's a trial and error procedure. As concerns the material properties adopted here, they are reported in this table, and we can see that there are two values for the yield stress. One is relevant to the core and another to the skins. We have determined these values on a real specimen through hardness test, and then correlating the hardness with the yield stress. And we will see in the next slide why we have these two values, why we have two different values. As concerns the contacts and the boundary conditions, a glue contact has been considered between the core and the skins. This solution is a good solution because another solution is to consider a shared node. So the same node of the skin is shared with the core, with the node of the core. But in this case, you need to design carefully the mesh, because you need the coincidence of the node on the boundaries, on the interface between the two parts. In this case, adopting a glue contact, you don't need this. And while another contact has been defined between the supports and the specimen, and between the loading nose and the specimen. The supports and the loading nose has been defined as a rigid surface, so no mesh is necessary in this case. No deformable elements are defined in this case. And we have adopted a sliding contact. The difference with the glue contact is that in both contact, the interpenetrations of the bodies is not allowed, but in the glue contact, also the tangential displacement, relative displacement, is not allowed, while in this case are allowed. So the specimen can slide on the supports. Okay. As concerns the experimental phase of this work, first of all, we have prepared a CAD, a CAD model of the specimen. In particular, we have used the materialized magics, that is a software able to build a lattice based on a particular cell in a specific volume. In this case, the volume is the same of the specimen. The skins were imported in the model by using a solid CAD, and we have used this solution so to have two different parts, because the specimen was produced considering two different sets of parameters. For the core, the net theme was used, while for the skins, the melt theme. These are two proprietary sets of parameters from the Arkham, that is the manufacturer of the machine that we have used. The part has been produced according to the ABM process, so it's a power bed technology. This is an image of the complete cake at the end of the printing. We have extracted, after cooling this part, we have extracted the specimen, cleaned them, and this is the obtained specimen. After the production, the specimens were tested according to the 3-point bending test as described before. Here there is a comparison of the experimental results with the numerical ones. In particular, we can see that both the numerical and experimental load displacement curves present the same shape. There is a first elastic part, a linear elastic part, followed by a pseudo-elastic parts, and then after the attainment of the maximum load, there is the breakage of the specimen. We can observe that the maximum load has been predicted very well, while the rigidity of the specimen, that is the slope of this first part, is a bit overestimated by the numerical model, as well as the transition point between the linear and the not linear part. In this image, I have reported a figure of the broken specimen, and we can see that the model was able to catch the buckling that has been verified under the loading nose. This is due to the high load reached in this zone. As concerns the crack, we have not simulated the crack, but we can see that the maximum, the zone where the maximum tensile stress has been reached is here in the lower part of the specimen, in the center. That is where the crack started. I have carried out also fractographies. We can see that there are dimples on the surface of this is an image of the lattice core of a beam. There are dimples, and these are due to shear stress. In fact, they are not, their direction is not perpendicular to the surface of the fracture, but is inclined. So this denotes shear stress. It also denotes a ductile behavior of the specimen. By comparison, this is a beam from a long beam, and we can see that they are not perpendicular. They are perpendicular to the surface, because in this case we have a normal stress, not shear stress. Finally, the metallographic analysis evidenced the two different microstructures for the core and the skins. In particular, the core presented a classical lamella alpha plus beta microstructures that is typical of this type of titanium alloy, while in the skins we have the presence of alpha martensite that is, we can see it in this zone. This because not only of the different sets of parameters, but also the different cooling rate. The skins behaves as a sort of fin, so the cooling rate is higher, while the core that has a lattice aspect is insulated by the powder that has not been melted during the process. These are the conclusions, so there is the summarization. I think that I have no time.
Okay, thank you. Thank you.
You're welcome. Thank you for your attention.